Hello guys, how you doing? Today is the last session of chapter 5 of Fluid Mechanics 1. I'm really excited about this because we have mm, made a really good journey in fluid mechanics. Today's title is the first law of thermodynamics and the energy equation. So follow me with the whole video. So, as I already told you, today's subject is the first law of thermodynamics, the energy equation, from section 5.3 of chapter 5 of Fluid Mechanics 1. Before going on instruction, I'm going to introduce myself. My name is Amir Reza Talaqat, and via email address amirrezatalagat@gmail.com, you can just send your questions, your comments about the video or anything related to the fluid mechanics, or you can just post it in the comments section of this video. I'll be so much delighted to give you the answers as soon as possible. First, we are going to talk about the first law of thermodynamics. It is completely related to the previous session, most likely the last session of chapter 4, which was about Reynolds transport theorem. Here we have a similar definition about the energy equation, which leads to the first law of thermodynamics. Here we have the material deviation of energy equation in Reynolds transport theorem, in which we have just substitute the small e, which is energy per unit of mass, in the Reynolds transport theorem as small b, which means the first law of thermodynamics is going to be gained as the time rate of increase of the total energy stored in a system is equal to the net time rate of change addition by heat transfer into the system plus the net time rate of energy addition by work transfer into the system. Something like this. In the equation 5.55, we have the net heat transfer in the system plus the net work transferred on the system. The energy itself has its own interpretation, which is the combination of internal energy, kinetic energy, as well as the potential energy. It's getting familiar with you in the following steps. It rings you the bell in following slides about a familiar subject which was instructed in chapter 3. Here we have the rate of heat transfer. Heat transfer, which is exerted on a system, is going to be defined as the plus sign, which is in which it's happening to increase the heat on the system, and it's going to be negative once we are just removing the heat out. Similar to the linear momentum equation, there's an instant in which the rate of heat transfer as well as the work on a system is equal to the corresponding one happening on the control volume, which is defined as equation 5.57. Here's the definition of energy equation in the Reynolds transport theorem based on the control volume as well as the control surface. They are just similar to the linear momentum equation by just substituting the small e as energy per unit of mass in this term, which was the small b. Here we have the small b as small e. I'm not here I have a point to tell you. As you see, we have the standard deviation of the system for the total energy. In this term, we have the control volume term, which is time dependent. And here we have the control surface term, which is having the dot product of the velocity and the normal of the surface. So all in all, the time rate of change of the total energy is equal to the time rate of change of the energy in control volume plus to the net energy flowing out the control surface in an instant that we are considering. So based on the equations that I've so far told you about, combination between equation 5.55 till 5.58 gains to be equation 5.59. So both sides are getting equal in terms of the derivation of energy equation. So the total energy stored in a system per unit of mass is equal to the net rate of changes for both heat as well as the work exerted on a system. It's completely valid for particles entering, leaving, or within the control volume. Once again, in this figure, you're just seeing how we have calculated the net the rate of changes of heat transfer getting in and getting out of the control volume. The ones that are getting out are shown with the negative sign, Q3 and Q4, and those which are entering are designated with the plus sign, Q1 and Q2. Having the combination of which is getting entered and which is getting out has to be remain zero. The net changes and the summation of them has to be remaining in zero amount because of energy conservation. There's the same concept for work exerted on a system. Guys, there are a lot of works exerted on a system. First of all, is the normal stress work. And the second to that is due to the shear stress. In order to give you an example, when you're having a pump, fan, or turbine, or compressor, or any kind of fluid mechanical equipment, there's a work which is exerted on a system as well as the control volume in a particular instant. As you know, the work is the dot product between the force and the distance traveled per unit of time, which is velocity. When we are dealing with the shaft, turbine shaft or compressor shaft or any kind of shaft, the work which is defined which we have is defined as the torque of the shaft multiplied by the angular velocity because it's turning. So the combination of the work which is getting in and which is getting out is the total shaft work, which is defined as equation 5.60. Guys, when we are having a work designated by a shaft, as we have a normal distribution, we are just analyzing the normal distribution of internal energy, kinetic energy, as well as the potential energy. The only force that is exerted on a control volume, as I told you in a previous session, is due to the pressure, which is getting a minus sign as equation 5.61 because it's just compressing the control volume from the outside. There's other work that I told you, the second type, which is related to the excuse me, it's in the next slide. Here, what's the point is that when we are having normal stress, which is defined as equation 5.61, we just replace the minus p in a small b term of the control surface term of total energy equation for system, which is defined as equation 5.62. There's a cosine of theta term because of the dot product of the velocity with the normal direction of the control surface. Here we have the tangential stress. As you know, when we are having a tangential stress because of the work, they are just happening in a surrounded control volume. They are going to be non-zero only where the velocity is in the centroid of the velocity profile, which is happening in here. Yes, yeah. The work of the tangential stress is defined as delta of a force of tangential stress multiplied by the V, which is the total work of shear stress. Yes. Guys, when we are having a work, as I told you, we are having two types of works, which is related to the normal stress, and the second to that, it's related to the tangential stress. However, when we are dealing with the tangential stress, when we most of the times we are having wet surroundings. In a wet surrounding, most likely in the limits or interfaces, since we have no velocity, there's no tangential stress. Coming to the centroid, when the velocity is getting past of the control surface, the control surface is perpendicular to the normal flow, to the velocity flow. So the cosine is equal to 9. The cosine of the theta is equal to cosine of the 90 degree, which is 0. So it means that all in all, we are just neglecting the tangential stress of the work term, and it's really logical because of the mathematical calculation. So the only thing that we are dealing in terms of work is the one that's related to the normal stress, which is shown in equation 5.63. Having more calculation, the total energy equation is going to be gained as equation 5.64, because this term is dislocated from this part to this part, which is going to get the plus sign in here. Yeah. Like any other steady state that we have already instructed, when we are having a steady state, the control volume term, which is time dependent, is going to be omitted. The same story is going to be happening in here. At the time which we are not having the v dot n as a zero term, and everything is uniformly distributed, we are having the total energy equation in a steady state as equation 5.65, which m dot is the integration of rho v dot n dA. Yes, there's the same story happening in here, which we are having just a uniformly distributed velocity profile in an infinitesimally small diameter. Yes. There's another story about the energy equation. When we are having compressible flow, these terms U and P are going to be combined together to form the other term, which is named as enthalpy. The combination of internal energy, and the pressure. If we have a compressible flow in a steady state, one-dimensional flow motion, the equation that we get is equation 5.69. You know, all of the times we're not having the steady state because there are fans, pumps, turbine, compressor, generators, or something like that. But for easiness, we're just considering them as a steady state, at least in this course. If you want to know more, we have to go further in the last chapters of fluid mechanics, which are related to chapter 11 and chapter 12. At that chapter, we are just knowing the unsteady state of energy equation. Here, I'm going to illustrate you both examples of 5.20 as well as the 5.21 in a written text to have you more familiar with the concepts that I've already discussed. So follow me with the written text. So, welcome guys to this session's first problem solving about example 5.20, which is subjected as energy pump power from section 5.3 of chapter 5. The question wants us to identify the power in the unit of horsepower required by the pump. At the initial step, we have to know what's getting entered and what's getting out. So we have to just apply the equation 5.67, which is going to be at the time average basis yield m dot multiplied by u2 minus u1 plus P over rho in section 2 minus P over rho at section 1 plus V2 to power 2 minus V1 to power 2 over 2 plus GZ2 minus GZ1. As long as we don't have any elevation, this term is going to be 0, and the total equation is equal to Q net in plus W of the shaft, work of the shaft net in. Since we are having adiabatic performance, it's going to be 0 in here. In order to identify the pump power required, we have to know the mass flow rate. So m dot is equal to rho q multiply, which is equal to it's 0 here, 1.94 multiplied by 3000 gallons per minute, which is defined in the question, multiplied by 32.174 lbm per slugs, divided by 7.48 gallon per cubic feet, multiplied by 60 seconds per minute in order to have all of them converted. It's conversion. So the mass flow rate is going to be 41.8 lbm per second. So, and for the velocity, we have to just know the, let me just see what I have answered. Yeah. For the velocity, we just have to calculate it based on the volume flow rate, Q divided by A, which is 300 gallon per minute, multiplied by 4, multiplied by 12 inch per feet to power 2, divided by 7.48 multiplied by 60 second per minute, multiplied by pi 3.5 to power 2. For the velocity at section 1, it's such a thing. For the section 2, we just need to substitute the amount of 3.5 with the 1. For section 1, for V1, we have the 10 feet per second, and for V2 we have just 123 feet per second. In here, W of the shaft is gonna be, this term is defined as 93 lbm per feet lb divided by lbm. Yeah. So we all have all of the information. We just need to substitute W of the shaft, W dot of the shaft in is equal to 41 multiplied by 93 minus 60 psi's as it's defined, multiplied by 144, the conversion of a square feet to inch square, divided by 1.9 multiplied by 32.174 plus this is plus minus just 80, and the whole thing again is written divided by 1.94 multiplied by 32.174 plus plus the 123 to power 2 minus 10 to power 2 over 2 of 32.174. This is gonna be multiplied by 1 over 550 feet pound per second and the horsepower. Doing the calculation, we're gonna have the horsepower of 32.2. So here we have the second problem solving of this session, which is about example 5.21, energy turbine power per unit mass of the flow, from section 5.3 of chapter 5. The question wants us to identify the work output involved per unit mass of a stream of steam through flow. We have to take the consideration at the first step as a steam for the steam turbine, its control volume, the appropriate one. We have to just use the equation 5.69 because we want to know the work and we want to identify what's getting in there and what's getting out. As long as we don't have any elevation, we don't write the z term, and also there's an adiabatic flow, so we don't have q net in. So the total thing is going to be m dot multiplied by h2 minus h1 plus v2 to power 2 minus v1 to power 2 over 2, which is totally equal to w net of the shaft in. If we it's gained as everything is divided by the unit of mass. If we have u2 minus u1 and the w net shaft in, these two terms are divided by unit of mass. So once we want to have the W net shaft out, it's equal to minus W net of shaft in. So this means that we have the H2 minus H1, which is 3,348 minus 2,550 plus v2 to power 2 minus v1 to power 2 over 2. This is going to be 30 to power 2, 60 to power 2 divided by 2, and it's going to be multiplied by the 1000 in order to get it converted here, excuse me. So doing the calculation, we have the W net of the shaft out as 797 kilojoule per kilogram. So welcome back, guys. Here I'm just illustrating you the difference between the time at which we have a work and time which we don't have a work. The only difference is due to the working term. Everything is remaining the same for incompressible flow as well as the compressible flow, at which for compressible flow we have enthalpy. For incompressible flow we have just the internal energy related to the pressure. In order to get it better, I'm going to illustrate you the example of 5.22 in a written text. So follow me with it. So here we have the problem solving of example 5.22, which is about the energy in the temperature change from section 5.3 of chapter 5. The question wants us to find out the temperature change associated with the flow, which is illustrated in figure E.22b. In order to solve this, we need to associate the temperature change with the internal energy change, which is going to be happening with a proportion. T2 minus T1 is equal to U2 minus U1 over C, which C is the specific heat of the water applied to the equation. It is 1 BTM over BTU, excuse me, over LBM degree of Rankine. So if we just apply it on equation 5.7t, we're gonna have this: m dot U2 minus U1 plus P over rho in section 2 minus P over rho in section 1 plus V2 to power 2 minus V1 to power 2 over 2 plus GZ2 minus Z1. It is going to be equal to Q dot net in, since we don't have any work. As the performance is adiabatic, it's 0, so this means these two are also equal. So they're going to be omitted. As long as we are having incompressible flow in atmospheric pressure, this means that V2 and V1 are also 0, so we don't have any V terms. So at the end of the day, we have the T2 minus T1 equal to GZ2 minus Z1 over C. This is equal to 1 BTU LBM degree of Rankine multiplied by 778 feet LB divided by BTU. So it's going to be equal to 778 feet LB pound over LBM degree of Rankine. So we have T2 minus T1 equal to 32.2 feet per square second, 720 feet as it's illustrated in the question, 778 multiplied by 32.2. So we have the temperature change as 0.54 degree of Rankine. Welcome back, guys. Here I'm going to illustrate you in more details about the energy equation. You know, guys, so far in equation 5.72, you're just seeing the steady state of energy equation in which we don't participated any kind of work. If we would just divide this equation per unit of mass, we are getting equation 5.73, which everything is in terms of deviation by unit of mass. Coming to the further, here you're just getting close to the familiarity with the previous chapter. They are getting related. As you may remember, if you have already seen the videos of chapter 3, at which we talked about the Bernoulli equation. In that chapter, the assumptions for Bernoulli equation were non-viscous, steady state, incompressible, and and the flow of the motion in a straight line. Here we are having the same thing because we have already neglected the viscosity effects. As you've seen here, the equation 5.74. We are having some terms of Bernoulli equation, in which we are added some terms which are defined as energy losses, available energy losses or useful energy losses. The term is the internal energy which is getting out minus the internal energy which is getting in minus the total rate of the heat transfer into the system per unit of mass. It's always greater than 0. Let me just, yeah. So we are having the last term in here. The fluid mechanical engineers are getting their best in order to minimize the losses ever. In order to get it better, I'm going to illustrate you the example 5.23 in a written text. So follow me with it. So, welcome guys to this section which is about problem solving of example 5.23. The subject is energy effect of loss of available energy from section 5.3 of chapter 5. The question wants us to compare the volume flow rates associated with two different vent configurations which are illustrated in figure E.23a. In order to do this, we have to go through the equation 5.79, which is P2 over gamma plus P2 to power 2 over 2 plus GZ2 is equal to P1 over gamma, excuse me, P2 over rho, P1 over rho, plus V1 to power 2 over 2 plus GZ1. Since we don't have any elevation changes, these two terms are going to be omitted. And also, it's a relatively big container, so we don't have any velocity at this first step. So, and the loss, there's a loss here. There's a loss here. I forgot to write it down. So, the V2 is going to be equal to square root of 2 multiplied by P at section 1 minus pressure at section 2 divided by rho minus the losses. The loss is defined as KL V2 to power 2 over 2. This is going to be illustrated in further sections. Here we have the KL as 0.5 because of the configuration for the two vents. So this is 0.5, and And let me just see what I have written. The Q2. If we just multiply everything by A2, we can have the Q. So we are gonna add it here, PD2 to power 2 over 2. This is 120 millimeters. So there has to be 1000 millimeter per meter at this side, and we have to just multiply everything by 1000, the pressure here, because it's in kilopascals, which is 1 kilopascal, and density is 1.23 kilogram per cubic meter, and the velocity of point 2 is let me see, velocity of point 2, it's not I forgot to write it down. It's 0.05 of v to power 2 over 2, so it's right. So we have compared everything. So this whole thing is gonna be 1 plus 0.05. It's not 0.5 here, it's 0.05. So the volume flow rate is going to be gained as 0.445 cubic meter per second, or if we just apply, I now remember what I have done. If we just write down the 0.05 here, the volume flow rate is going to be gained as 445. If we just replace it by 0.5, the volume flow rate is going to be gained as 0.372 cubic meter per second. Welcome back, guys. Here we are just participating the work of the shaft in the equation 5.80, and just like previous step, it's divided by unit of mass as equation 5.81. The losses are calculated, and total energy equation is gained as equation 5.82 per unit of mass. Yeah, guys, as long as we have a work or we don't have a work, there are some losses. It depends how it's getting acted in, it's getting worked or gets acted on the system. For example, when we have a work, there's a work term in here, which means we have to adjust the previous energy equation in the first stage in a more amount to be adjusted with the second stage in order to get the conservation of the mass and the conservation of energy. Once we don't have a work, it's getting the same concept because of the loss. Loss are existing in every instant and permanently. But when we are having a shaft or work of the shaft, it means we have to just pay more work on a system in order to get the second and the first stage in more balanced way. In order to get it better, I'm going to illustrate you the example 5.24 in a written text. So follow me with it. So here we have the problem solving of example 5.25, which is about fan work and efficiency from section 5.3 of chapter 5. The question wants us to determine two things: how much of the work of the air actually produces useful effects, that is, the fluid motion and a rise in an available energy. Estimate the fluid mechanical efficiency of the fan. So Here we have to use the figure E5.24 and also the equation 5.82, which is W shaft in net in minus losses is equal to P2 over rho plus V2 to power 2 over 2 plus GZ2 total minus, excuse me, let me just write it over here, P2 minus P1 over rho plus V1 to power 2 over 2 plus GZ1. Yeah, that's it. Let me just enhance the light. Yeah. These, as long as we have atmospheric pressure, these two terms are going to be omitted. We don't have any elevations, these two terms are going to be omitted. And the container is very big. We have the velocity at the first stage as 0. So the whole thing is going to be equal to this. So this term is going to be equal to this term, which is V2 to power 2 divided by 2, which is 72 Newton meter per kilogram. In order to have the efficiency, we need to know the mass flow rate, which is by dividing the total W of the shaft in net to it, we're gonna have the W shaft in per unit of mass. This is equal to rho AV, which is rho pi D2 to power 2 over 4 V2 multiplied by V2. This is 0.4 kilowatts multiplied by 1000 to be converted. And here we have 1.23. D2 is 0.6 meters and the V2 is 12. So the W shaft per unit of mass is equal to 95.8 Newton meter per kilogram. The efficiency is 72 divided by 95.8, which is 0.752, or in other words, 75.2%. Welcome back, guys. Here there is an enthalpy term and definition of the energy equation. If we have the equation 5.83, which is per unit of mass, multiplied by the term of the density of in order to define the energy equation, once we divide it by a gravity acceleration in equation 5.84, we are just having the head term, which are exactly the losses, but they are defined in terms of head. For work term, which is defined as capital W of the shaft divided by units of unit of mass, which is a small work in here. Once we divide it by G, as it is capital W divided by m dot multiplied by G. M dot itself is rho multiplied by gamma. Once we have it as this, it's just the term of the HS, which is head loss of the shaft work, defined as HS. And HL is the loss divided by G. Let me just adjust the slides. Yeah. In this figure, you're just seeing the effect of the head, whether it's loss or what's due to the shaft. Once we don't have any losses, the heads of the in and the outlet are same. Once we have the head due to the loss, it's the head of the outlet, it's less than the inlet. It's just based on the calculation which you see the effects of the head losses of the shaft or the loss due to itself. In order to get it better, I'm going to illustrate you example 5.25 in a written text. So follow me with it. So guys, here's the last example of session of this session and total examples of the chapter 5 and also the total examples of fluid mechanics 1. The question wants us to identify the flow rate and the power loss associated with the flow in the figure of E525A. For this assignment, we have to use equation 5.84, which is P2 over gamma plus V2 to the power 2 over 2Gs plus Z2 is equal to P1 over gamma plus V1 to the power 2 over 2G plus Z1 plus HS minus HL. So as long as we are in the surface, we don't have any P's. So, and the containers are so big, so we don't have any velocities. And the whole thing is going to be HS is equal to HL plus Z2 minus Z1. Here's 30, it's 0. HS is equal to total work of the shaft net in divided by gamma Q. This is 10 multiplied by 550 to be converted, and gamma is 62.4 pound per cubic feet. So we have it as 88.1 divided by Q. If we just substitute it here, we're gonna have the Q as HL is itself is equal to 15. Q is going to be equal to 1.96 cubic feet per second. And the power loss, the W dot of loss, is going to be equal to gamma Q HL, which is 62.4 multiplied by 1.96 multiplied by 15, which is gonna be divided by 550 to be converted to horsepower, and the horsepower is gonna be 3.33 horsepowers. So welcome guys to the last part of chapter 5 of fluid mechanics 1. I'm really glad that you have accompanied me till this moment of this video. And I'm also happy that you have already been through the previous videos about the fluid mechanics. Here's the end of the fluid mechanics 1 in the first phase. Second to that, in near future, I'm going to instruct the second phase of fluid mechanics, which is fluid mechanics 2. Please don't hesitate to ask your questions, whether they're fluid mechanics related or related to these videos. I'll be so much delighted to give you the answers as soon as possible. And most importantly, please subscribe the channel in order to get the notification of all upcoming instructional sessions. I bid you our farewell. See you in the next future.